Okay, we're going to continue this trend of experts talking about um, challenging, difficult, and certainly very progressive ideas. Jeff is going to talk about improving SiP quality and reducing costs through the use of machine learning and predictive analytics. I can't think of anybody more qualified to talk about this. Jeff brings over 20 years of experience from PDS solutions in in the AI area. Prior to that, he was CEO of Stream Mosaic, which focused on AI and machine learning. And then before that, he was at Applied Materials, where he did systems, algorithms, and for manufacturing quality and efficiency. Incredibly, Jeff has authored or co-authored more than 90 US patents. I haven't talked to anybody recently anywhere close to that. Jeff has an MS in interdisciplinary engineering and a BS in electrical engineering from Purdue and an MBA from Indiana University. Jeff?
Sorry, I had to take it off mute. Thanks, Dave, for the introduction. Yeah, so today I'll be talking about, a very important topic, improving system and package quality and reducing their costs with machine learning and predictive analytics. So yeah, I've got a lot of content to go through that I'd like to share today, so let's get right to it. Okay, so here's the legal stuff. Okay, so the more than more era has ushered in a multi-chip, system and package modules and chiplets. And there's a lot of value that can be realized by taking this approach. Yield improves due to smaller individual die and package. So killer defects on a wafer lead to smaller yield hits. Also, you don't need the latest device node for all the aspects of your chiplets, such as the I/O interface. Older device nodes will be cheaper and the overall process more stable, which leads to better yield and performance. Additionally, the overall design cycle is shorter as you're not reinventing the wheel and leveraging pre-existing work. It's also worth noting that the manufacturing cost can be lower with a commercial marketplace for known good die. And, of course, there's a manufacturing cost advantage when the same chiplets are used in many designs. So, that is the value proposition is very promising. But, companies face challenges controlling the cost of these complex devices while meeting their customers' stringent quality requirements. Companies also face compatibility and integration challenges due to interface standardization. And, data complexity is also an issue since you have to deal with the alignment of data coming from multiple chips rolled up into one module. So, how do you align all this data to make use of it? This is a real challenge. There's also more opportunity for hardware Trojans since chiplets will be developed by third parties. It's a lot harder to confirm a chiplet isn't doing what it's supposed to be doing if it's part of a heterogeneous solution. So, net is the value is very promising, but we got some challenges. Okay, so, like I mentioned, there's a lot of challenges to meet in manufacturing SiPs. Conventional test techniques aren't cutting it, and all too often fall short of realizing acceptable quality levels. So enter machine learning. Machine learning excels at predicting device quality as large quantities of parameters are considered simultaneously. As we've often heard that ML is only as good as the input data that is fed into these pipelines, it can also be said that ML is only as good as the platform it's run on. Especially true for SiP manufacturing given the added complexity of data integration flows and storage. So, in this talk, we'll explore the application of modern machine learning techniques to predict devices at risk while concurrently, expediting, reducing tests for die with little risk of defectivity. and the residual cost test that can be invested to more thoroughly screen devices exhibiting marginal quality to increase overall outgoing quality. So, in parallel with these efforts, companies are also implementing end-to-end integrated database approaches that include, not only traditional test data, but also includes wafer, die, and package traceability data. And I'll be touching a little bit on that later in the presentation. So we'll discuss how a combination of additional data sources enables machine learning applications to expand their quality prediction capabilities beyond test operations. Okay, so quantifying predictive power. So one of the first things we always do when applying ML to semiconductor manufacturing data is to investigate the predictive power and the data available. Either formally or informally, you're always going to have to do this. So, this can be thought of as how well the input data that you're putting into the ML pipeline correlates with the target variable that you're trying to predict. So, there's a few different types of outcomes from this exercise. So let's say that you determine that the predictive power is low. Then we need to look into identifying tests that are more predictive. Is there ways that we can bring in data that is more predictive than what you currently have? This can be based on past experiences, some tribal knowledge. Engineers have ideas of ways to do this and what they believe is predictive. So let's say that you start off with a much better picture, as if the predictive power is sufficient. Then you proceed to the relevant solution. Some of which I'll touch on later in this talk as well. These solutions could be things like predicting whether or not a die will pass an expensive test, or determine if a die should be screened out, after wafer sort. Or we can recommend if more data is needed, if we determine, the sample size is too low. So what if your test data set doesn't have enough data to be able to confidently say that you're going to be able to do whatever your intended use case is? Another way to think about this, if we believe correlations we are seeing are by chance, or if they're statistically significant. So this is something, it's another important aspect you have to wrap your head around early on. Okay, so what I'm showing here is, kind of an example of a ML pipeline. So once you've determined that your data set contains predictive power, then you can apply an ML pipeline to your data. So here I'm showing, on the top horizontal, what would be considered the training pipeline, where you actually train your model. And on the bottom here is the prediction pipeline, also commonly referred to as inference. So, each one of these pipelines has a little bit, different aspects to them, but there are some similarities. For example, you always have to do the feature engineering up front, transforming your data into other engineered features that are more meaningful to your machine learning pipeline. You do that both for training and prediction. You want to do some amount of feature selection from your training data sets. So if you have hundreds of thousands of inputs, how do you whittle that down to something that's more manageable? You might also want to do imputation to fill in, some holes in your data, as long as your data isn't too potholed. You might want to do some grouping together of different inputs. Then you might want to do something more along the lines of multivariate feature selection. So if you do on a univariate basis your feature selection earlier on, you would want to do a multivariate feature selection, so you take into account the interactions that these separate input variables may have with each other. So then, after that, you go on to, the actual building of the model, handling imbalances, which is a real problem I'll talk about later with the data sets that we deal with. Then down here, the prediction pipeline, A lot of the same, except now you have your model generated. Now it's just a matter of how quickly, or how fast you can make that prediction. And this is going to depend on the specific use case that you're doing this prediction for. Okay. So, oh, did I skip one? Yeah, sorry, skipped one. Okay, there we go. All right. So ML pipelines can be constructed and applied in different ways to solve different types of problems for different use cases. So, here's a few examples of some of the solutions, built on PDF's Exensio platform, that leverage ML. And of course, as I mentioned earlier, the success of these solutions relies not only on the available analytics, but also the data readiness and predictive power that you have in that data. Okay, so let's go through a few of these. With smart testing, we're able to predict if a die will pass at a given test insertion. And if we predict it will pass, then some amount of chip volume at that test insertion can be skipped altogether. So you can imagine that this could be very valuable for some of these more expensive tests. And this is done using upstream data, such as PCM, wafer sort, even further upstream into the fab. With FPM, fab predictive modeling, we predict yield at both the die level and the wafer level. Now, what we've seen, our customers are really interested in is a big benefit of FPM is that we're able to home in on the root cause of failures all the way down to the sensor level on tools and chambers, if that data is available. So you can imagine the huge value in this and being able to, short circuit that whole root cause process. We're able to quickly identify what the root causes of failures using data that you're already collecting. Okay, with ASD, we're able to classify wafer level with different types of failure patterns. For example, different types of failure clusters on the wafer, or an asymmetric edge issue, all different CMP scratches, all these different types of things, and then use use this information in ML to identify the root cause of those failure patterns using ML. Okay, so with IMD, we're able to predict the quality of the wafer using upstream data for more efficient wafer dispositioning. ELF, I kind of, we call it ELF, early life failure detection. We leverage advanced outlier detection techniques to screen out bad die with the lowest possible overkill. And I'll do a little bit of deep dive into ELF in the next few slides. Okay, so here's the ELF slide. So let's do a bit of a deep dive into ELF. So the goal of ELF, which again stands for early life failures, is to reduce the number of RMAs, or in other embodiments, burn-in failures, for example, by efficiently screening out bad die at wafer sort. We do this essentially with our advanced anomaly detection techniques. So, on the left, what we're showing is the different types of data we ingest to predict which die will fail. So you got all different types of data here that you can ingest. From there, it's passed to our ML pipeline, powered by Exensio. From there, anomaly score is provided, after it runs through this engine, where our customers can choose what to do next, right? They may choose to downbin the chip. As Jan was mentioning earlier, there's a lot of value in doing that. They may choose to test it more or to review it, or they may choose to scrap that chip altogether, right? Okay, so what we also allow the user to do is we allow the user to feed back to our ML engine via what we call collaborative learning on our Exensio platform, which refines the predictions through continuous feedback of the system. So what we're doing here is incorporating human feedback into the results we get to produce better predictions later. So this is an area that we've spent a lot of cycles on recently, and we really see the value in allowing engineers and experts add their input to the ML predictions. You know, in ML, this you know, is also referred to as active learning. Okay, so you know, I think it's important to note that different types of use cases and different types of data sets require different types of algorithms. You know, there's no single ML algorithm that's going to do that's going to work best for all situations. And, you know, this concept expands out to something I'll be talking a little bit more about in the coming slides. This expands out as well to anomaly detection. You know, so with respect to one algorithmic approach solving all problems, there's really no free lunch here, right? You have to have, you know, you have to have different tools at your disposal for different types of situations. Okay, so we can expand this out to choices in the broader ML field with respect to, you know, supervised learning versus anomaly detection. So those of you who are familiar with anomaly detection, you're probably most familiar with anomaly detection from the unsupervised sense. But you know, you can also think of it. There's embodiments of semi-supervised and also supervised as well. So why is it for ELF? You know, again, our early life failure solution. Why is it we've chosen to focus within the field of anomaly detection to address early life failures? So anomaly detection is designed to work well where there's predominantly single normal class with a few abnormal classes that are extremely low in data volume, right? So you can think about, you know, this is certainly the case for predicting, for example, an RMA or a Vernon failure, where, you know, you may have a situation where your data population, you'll have a few failed parts per million or even per billion. So that means that most of your chips are going to be deemed normal, but there's just going to be a few out of a million per billion that you need to capture. So, you know, from an ML perspective, this is a very, very challenging problem, right? And this can be thought of, you know, that this data set is highly skewed, right? And it really drives what kind of approach you do. And even though, you know, supervised techniques can work well in this situation, what we've found is that a lot of times anomaly detection is better suited. So let's go into a little bit more there. Okay, so I really like this slide. This is a fun slide. So what we're showing here is how some of our anomaly detection techniques perform with a toy data set that we developed to really dig into how these different types of algorithms work. So what we're showing here is a comparison of what we have here is robust covariance on these 5 different flavors of data sets that we've created to our different multivariate techniques that we've developed that, you know, we've called here for the sake of this presentation MV1 through MV5. So, you know, and you can see that each one of these algorithms performs differently against different types of data sets, right? We have the case of a single, somewhat normally distributed cluster with some outliers. So here's probably what people are, you know, this is the most standard type of distribution. But we have something a little bit more interesting here. You know, it's a binomial distribution of equal densities. We also have a bimodal distribution with different densities, a bimodal distribution with nonlinear relationships, and a distribution that's largely random, right? So how do our different techniques perform against these different data sets? And for each of these, we're showing how the algorithm chose to split between what is considered normal, which is denoted by blue, and an anomaly, which is denoted by orange. So this is how the different algorithms are making the splits. Blue, the algorithm says that it's normal. Orange, the algorithm says that it's an outlier. So really interesting to see how these different techniques work. You know, here the covariance does great in this situation, starts to fall apart, you know, as you go down to some of these other data sets. And, you know, depending on the distributions, different techniques perform better than others. You might say overall that MV3 and MV4 are doing, you know, somewhat better job. This technique, MV2, doesn't capture these failures right here in this nonlinear data set. Maybe MV3, you might say that some of these points right here should be included in the normal data set. This nonlinear anomaly detection technique, it's hard to see, but you might argue it's not doing that bad of a job, right? So yeah, fun slide. I really like this slide.
Is MV5 even in control? It looks out of control.
It is. You'd actually, this is, a lot of people like this slide, this technique. This is a nonlinear anomaly detection technique. And, but yeah, the way that it draws the boundaries does look kind of interesting, right? So very, yeah, this picture speaks 1,000 words, right? Oops. Okay. So for more of our data-driven folks, it's probably most of us are here, let's go into some results with an actual production data set. Okay, so let me first set this slide up a bit. Okay, this is an actual production data set, and it's important to note that some amount of screening was already done to this data set before we ran the analytics on it. So what we're showing here is what if you applied our MV techniques beyond the initial screening, right? And we're also including DPAT as a baseline. So essentially what you're doing with DPAT is you're expanding out the N sigma to be able to include more percent fallout, and how many of these failures, you know, you can think of as RMAs or burn-ins, are you catching as you expand out this population that you're throwing out, right? You know, so what we're showing again in this graph is how many more failed die capture for a given amount of fallout with our advanced ML techniques. You know, where the x-axis is percent fallout, which for you ML folks out there is synonymous with FPR or false positive rate. And the y-axis is capture rate, which is synonymous with TPR or true positive rate. So net, you know, on a relative basis, you know, what we're seeing is significantly more failures were captured, you know, with our MV technique. And I didn't want to clutter up the slide with all the MV1 for MV5s. I just put the best one, which was MV3 in this case. We were able to capture more of the failures in, you know, equivalent amount of population, more than DPAT, you know, in any given fallout percent.
So Jeff, you know, a 35% capture rate, you would, you know, how's that compare? I mean, you'd like to catch them all, but it looks like diminishing returns, but at 35% of capturing the defects seems low, you know?
Yeah, so yeah, I would love to be able to tell you, to sit here and tell you that we can capture every single failure. So, but, you know, if you're finding a failure as something like a field return or an RMA or burn-in failure, and if you define the base chip population as the remaining good die after wafer sort, you know, then screening out 80% of failures with 5% fallout without doing anything else, then applying ML to data that you're already collecting, it, in my opinion, is not currently possible, at least based on the, you know, more than several data sets that I've worked with, you know, based on analytics only. You know, that's my opinion based on more than several data sets that we've come across. But, you know, you can decide for yourself, right? There are lots of reasons for this, that why we can't hit 80% with 1% fallout. some of them, mainly because there are a significant portion of failures that have little or no correlation to upstream data. You're never going to capture these things, right? Unless you really invest the time into creating the data that you need in order to be able to see these failures. In other words, it may not be possible, given the data that you have, to predict every last failure, no matter what ML technique you employ, because the data just isn't there, right? I focused on this and a path to address it in the earlier slide, I had on predictive power. Other reasons include, operational difficulties in maintaining a clean and complete production data set. Really puts a lot of onus on that. Not going to be spending a little bit of time on that, in some future slides. Yeah, around, which the analytics can be built, right? So, yeah, so that's kind of my long-winded answer to a fair question. So.
Thank you.
Yeah, Jeff, if I can jump in while we're here,
forgive me.
But how do you determine false fails? In other words, finding failures is good, but what if you're failing some good parts?
Well, yeah, that's captured in the fallout, right? So basically, if you say that a chip is bad, but it was actually good, then you may end up throwing that chip in the trash bin, right? Or down binning that chip. That's captured in the fallout. So basically what we're saying here is, given on the x-axis the percent of fallout that your cost for improving your quality, how much fallout are you willing to pallet to capture these RMAs or to capture these burn-in failures, right? Before they come back and bite you, right? So if you can say, okay, I'm willing to throw out 2% or downbin 2% of my data to, capture 10% more fallouts than what I was already doing, or I'm sorry, more failures than what I was already doing, that might be a cost that you're willing to live with. So you decide. Basically the customer decides where it is they're comfortable living on this curve. They may say, hey, I'm very sensitive to RMAs. I'm okay with sacrificing 6% of my chip population in order to reduce my field returns by a third, right? And also, I really want to emphasize here that, this data set is, it's after, their already standard screening techniques were employed, right? So they employed, some screening techniques. They already threw out some dye. Presumably they threw out a lot of bad dye, along with some good dye too. So there's already some pruning that's been done to this data set. So what we're saying is, hey, if you took an industry standard technique and, we chose DPAT to be our industry standard technique, and we expanded that out, how much better would our techniques do compared to DPAT on this already screened data set? If you ask me to really do this experiment, is to partner with somebody that's willing to not screen out any of their dye up front and apply this. That's obviously a very, very expensive endeavor to do something like that. But here, what the hope is that we can get our customers wrap their heads around the power of multivariate anomaly detection by comparing it to something like a univariate anomaly detection such as DPAT, right? So yeah, so this is, you have to spend some time wrapping your head around this thing, but to me, I find it very compelling. Okay, so moving right along. So, now I want to shift the focus from the ML pipeline and to the analytics platform itself, right? Because all these things are important, right? It takes more than just a solid ML pipeline to be successful. No matter how powerful your data, sharp your data scientists are, at the end of the day, you have to be able to deploy, you have to have the right platform that can work robustly, in a semiconductor manufacturing environment. You also need a scalable system that can handle all the data types. merge and cleanse that data, build semantic models that build, the right types of relationships between the data. And that can make sense of these complex data structures, especially, we're talking about here system and package. We have multiple die in a package. Our experience is, there's an added level of complexity here in merging all these different data sets together. It's more challenging, right? Yeah, so, again, this is especially true for SiP. You might also need to create new data types that weren't previously available. For example, like some tables that, PDF offers, right? And having access to all the data end to end and building traceability, right? So, Dave Greenlaw touched on this a little bit, in his keynote, that being able to trace the data, all the way through the process is key, right? And putting in place, again, the right semantic models that will give you the best probability of success. Okay, so having a platform that can integrate all fab and backend data and provide the right types of visualization important. This is what's happening with the Exensio platform. We have the right types of visualization. You can do, high volume product analysis as well as new product introduction. We feed the data into and out of our Exensio yield platform. Okay, and having a good way to get the data into the platform is also important. So, at PDF, we offer what's called the data exchange network, also known as the DEX network. Which allows our customers to pull in data from different sources across the world and assemble it into one place. And also across different companies as well. It's very important. For example, we assemble data from the fab, the OSATs, the fabless customer, all with our DEX network. Allowing our customers to leverage all this data and take action to improve their quality and yield. Because, at the end of the day, the data, is the foundation on which, a solid ML approach is built. So having that data there assembled, ready to go, in a situation where you're pulling it in from different companies, that's critical. Okay, so it's worth mentioning that the data that feeds analytics is usually limited to wafer fab and test and final test, these types of things. What doesn't really get talked about a lot and has kind of been treated as a black box is package assembly and subsequent board assembly. These from what I'm sensing hasn't gotten the attention that it deserves. And I think we need to change that, especially if we're going to do, Dave or Ira, getting to that 80% failure point. We really need to collect data from all these sources. And lot level traceability is not good enough. You need single device traceability, which gives you insight into assembly, which is critical. Tracking the journey of a single die and package through assembly allows us to trace from the final package at test back to assembly steps and equipment used to assemble it, all the way back to the XY location, on the wafers where all the die were picked from. Yeah, so note, that this must be possible to do without ESID. So ESID, lacks the traceability to assembly steps and is not even an option for, a significant number of die. Once you have, the single device traceability, also known as SDT, it is possible to pinpoint each equipment used in exact process variables and traces that were recorded at that time. The estimates from different sources vary. I couldn't, home in on an exact number, but let's just say, a significant portion of field failures are traced to assembly related root causes. With SDC, it becomes possible to collect a rich and precise data set that enables analytics to rapidly pinpoint the problem. tracking, from, what I'm showing here, the die attach equipment, you can capture the batch of epoxy. You might have a bad batch of epoxy and the batch of gold wire, which can be used. You can use all this information to track down failures. We do have some experiences here, with the equipment, with some of the equipment shown here in this slide, that we're able to track down failures to this equipment, right? So this is key, as our customers are challenging us to help them drive down their DPPMs and DPPB, B as in billion, down to 0, right? You've really got to take into consideration these things, right? Also, as I was saying, we can find problems with wire bonding at the source. All these assembly tools have variables where we can identify failures. We need to be able to trace the device through assembly to enable the traceability all the way back to the wafer, all without access, potentially without access to ESED. As the devices, as I mentioned, may not have ESED. If you don't have ESED, it doesn't make the traceability any less important. Okay, so, in summation, I talked about, how SiP raises the stake for quality, final test yield, assembly, traceability, and diagnostics. And, of course, ML can untangle the complex relationships in SiP data, enable AI for yield and quality improvement, at reasonable costs. The right machine learning algorithm and approaches needs to be chosen, as no single algorithm works for all different use cases. And I did a little bit of a deep dive into that around our advanced anomaly detection, advanced outlier screening techniques. And just as important as an end-to-end analytic system that enables all this, test data, assessment, optimization capabilities. These are elements that are essential for success. So thank you very much for your attention. Thank you.
Thank you, Jeff. We really have run out of time, but there's one question here I'm hoping you can maybe give a 1 or 5-word answer to.
Yeah.
And that is, what's the phase of machine learning in ELF? Has it been implemented in production yet?
We have, so we do have some customers who are exploring it. Exactly where it is in production, maybe. Let me say that.
Soon.
Soon.
Okay. Thank you.
Yeah.
Thank you, Jeff.
Yep. You're welcome.
I'd like to thank all the speakers, and I'd like to thank everybody who's attended. I think we've had great participation, a lot of interaction, some really great questions. Also need to thank our sponsors who've made this event possible. ASC, Advantest, Gelpack, Muhlbauer, Amcor, and Microcircuit Laboratories. Our diamond sponsor is ASC. They provide OSAT and EMS services, the whole range from design, assembly, test, materials, components, and logistics. And then we also need to thank Advantest with over 30,000 installed ATE systems worldwide, deep expertise, a large workforce, and been in the measurement arena for over 60 years. So thank you, Advantest. Also, thank you to Gelpack, whose goal is to protect the world's valuable devices, both in manufacturing and in process and in storage and in transport. So Gelpack, we appreciate your support. And lastly, we thank Muhlbauer, whose specialty is factory automation and data to drive the manufacturing process. So we thank Muhlbauer for their support. Once again, I thank everybody for attending. I hope everybody found this a worthwhile and informative event. Please send us your feedback. I'd love to hear it and hope to see you at a future MEPTEC or event and in next edition of Known Good Die Workshop next year. So I thank everybody and I wish you a good remainder of your day. Thank you.